Good afternoon, everybody, and welcome to the Heidelberg Joint Astronomical Colloquium. And it's really a particular pleasure and privilege to introduce today's speaker, Professor Ken Farley, who is the project scientist of NASA's Mars 220 rover mission and professor of geochemistry at the California Institute of Technology. Ken received his Doctor of Philosophy degree in 1991 at the University of California at San Diego. And this was followed by postdoctoral positions at the University of Rochester and at Columbia University, after which Ken came back to California as an assistant professor of geochemistry at Caltech. That was in 1993. And pretty soon afterwards, in 1998, he was appointed as a full professor at Caltech. Ken's primary interest was noble gas isotopes, and I think still is, I guess, and their application to a wide range of earth science problems. But this developed towards the geochemistry and geochronology of Mars, in addition to that of Earth. And he was a participating scientist in the Curiosity Mars rover mission, which landed in 2012 on Mars. Ken's the recipient of numerous awards and honors. I'd just like to pick out here his appointment in 2003 to the W.M. Keck Foundation Chair of Geochemistry at Caltech, and also his election to the National Academy of Sciences in 2013. I think 2013 was also more or less the starting gun for the Mars 220 rover mission and Ken's appointment as mission scientist. And as we all know, at least most of us on planet Earth are aware of, this culminated in the landing of Perseverance on February the 18th this year. So now we all look forward to hearing from Ken about the results obtained on Mars since then in your colloquium entitled 10 Months of Perseverance on Mars. Thank you.
All right. You see my screen okay?
Yep.
All right. Well, I didn't update my my title slide. It's actually 10 months, not 9 months, but who's counting? Yeah, so I am a project scientist for the Mars 2020 Perseverance rover mission. And I have been in this role since the inception of the mission. And what that means is that until we launched in July of 2020, I worked with the engineers to design and implement the spacecraft. And then when we got to Mars, I'd lead the science team. So I want to tell you a little bit about the purpose of the mission and what we have discovered so far, recognizing that this is likely to be a very long mission, could last upwards of a decade. And it's early days for us. We have been on Mars for 285 Martian days as of today. So I'll tell you about what I think we have found so far and tell you a little bit about what this journey has been like. It's been a very interesting experience for me personally. I'll tell you a little bit about that. Okay, I want to start with what for many of you, it could be the only thing you know about this mission, is that we landed successfully. As the engineers told me from the day I started this job, the highest concentration of risk for this mission comes down to a few minute period when you're landing on Mars. And I want to show you how this worked because it's truly spectacular. I'll start with this image. So this is an orbital image draped over topography, which should immediately tell you we have really, really good information from orbiters. So we're not landing in the blind. We know a lot. And I'm going to show you a video that is taken from the spacecraft during landing. One of the really interesting things that we decided to do during development was to include 6 different cameras on the different components of the descending spacecraft. These were essentially commercial off-the-shelf cameras. They were not built for this purpose. You know, many things, if you want to fly them in space, have to be built for all sorts of stressful conditions. These were just commercial cameras that we stuck on the spacecraft to see if we could record entry, descent, and landing. And it was spectacularly successful. So I'm going to play that video, but let me give you the context. So here, what you're looking at is the landing site called Jezero Crater. The crater rim is off to the left here. This big feature that you see, I'm going to talk about in detail, is the delta, telling us there was once a lake here. And very conveniently, this crater is about 1 kilometer across. So you get the scale of this feature. We thought we were going to land somewhere. We had an error ellipse that was like this big. But given that we had the ability to steer during landing, to land in the safest possible place that was reachable, everything suggested that we would land in this area here, which you can sort of see looks pretty flat. We called this the landing strip. We thought we were going to land here, and we were pretty excited about that because the highest value science target was the delta. We thought we were going to land here. We actually landed here, and the little piece of video that I'm going to show you, you'll see how that happened. So you will see in the video the delta with its 40-meter high cliffs. You will see this strange feature here that I'm outlining. It's kind of shaped like a mitten, called seta. It has this kind of corrugated texture that you see with ridges running this way, and it's filled with sand dunes. And in particular, you will see this crater, which we call Hahutsa. These are names that the science team attached to these. So let me play that video. Oh, and remind you how we actually land. So we are coming in on a ballistic trajectory from Earth. There's no orbiting Mars. So we reach the Martian atmosphere traveling at a little over 4 kilometers per second. And we, in about 7 minutes, need to shed all of that velocity and touch down at essentially 0 velocity on the surface. And this is a challenge on Mars because if you only tried to use a parachute, you would reach the ground with too high a terminal velocity. The Martian atmosphere is too thin to just go on parachutes. You need a retrorocket stage. On the other hand, there's enough atmosphere that you can't do it just with retrorockets because you would burn up when you hit the atmosphere. So you have to do an aerobraking step. So this is a piece of the video that you can find on our website that records the whole 7 minutes of this. It begins with the rover as well as the retrorockets all bundled up inside this shell. And then so this shell both aerobrakes and steers. Ultimately, we needed to have the ability to land in an area that was about 5 kilometers in diameter. So we had to do a lot of active steering to land at the right place. So we aerobrake, we pop the supersonic parachute, and then we drop the bottom heat shield. And ultimately what happens is the rover and the retrorockets drop away from the parachute. So this piece of video picks up just as this is called the descent stage, just as the descent stage drops out of the back shell and the parachute and goes into free fall. It's going to fire up the rockets. And while it's doing this, it is deciding where the safe place to land is. So it knows from imagery that we gave it where it is safe to land and where it is not safe to land. And it's fascinating to see what happened here. So this is the start of the video. This is actual real imagery from the spacecraft. It is rotated by 90 degrees from what I showed you a minute ago. So this is the front of the delta. North is in this direction. So this is the 40-meter high cliffs of the delta. This is the landing strip where we thought we were going to land. And you will see, well, it may be hard to figure it out. The spacecraft determined that we could not land here, and it had to make a decision about where we would go. So here we go. So we're not going to land here. Here's the big crater called Hahutsa. Here's that area called Seta with all the sand dunes. Can't land there. It swings over here. We cannot land here either. And I'll show you a picture from the ground. This is filled with boulders. no good landing here. It found a very narrow strip for us to land. And that started at about 2 kilometers elevation. We're falling very fast. And now you can see the sand dunes. You'll start to see the retro rockets interact with the dust on the surface. And then here's real video of what's called the sky crane maneuver. So the rover is literally winched from the descent stage with its retro rockets. It's winched to the ground. And as soon as the wheels touch the ground, some pyrotechnic bolts cut the bridle. And then the descent stage, we need to get it out of the way. We don't want to tangle up with it. So it flies away. It winds up crashing about 1 kilometer away. And at the end of the day, what you wind up with is the rover sitting completely free of all debris on its wheels, ready to go. This is an image from orbit showing from the Mars Reconnaissance Orbiter. This is actually the rover sitting on the ground. Here it is blown up. And you see this butterfly pattern. That's where the retro rockets blew the dust off of the surface. So we called this the Octavio Butler landing after the author, which is a tradition. And you can see we landed between sand dunes that are both not landable and not traversable by the rover, and a boulder field, a very large boulder field, not landable and not traversable. We landed on this narrow strip. And when the reconstruction of how this landing worked was investigated, we landed within about 2 meters of where the descending spacecraft suggested we should go. So it's very promising that in the future, pinpoint landing, well, it demonstrates that pinpoint landing is possible. If you have the fuel to do it, to fly to where you want to go, pinpoint landing on Mars is possible, which is enabling for many kinds of things, human exploration for one, more importantly for this mission, for the collection of the samples that we are collecting. I'll talk to you more about that. Super successful landing. You can imagine how exciting this was to to all of us to land. A little puzzling where we landed, and that has completely shaped what the mission has done since then. Okay, so let me give you the backstory of what we're trying to accomplish and how we're trying to do it. So the Perseverance rover is a rebuild of the Curiosity rover. So huge technological developments went into building Curiosity, which as you heard in the introduction, was launched landed in 2012. We rebuilt it with new science instruments and some fundamentally new capabilities to meet our science goals. But we have the advantage that we are version 2 of this. And so we learned a lot from Curiosity about both how to build this and how to operate it. Our goals are to seek evidence of ancient Martian life, and I'm going to explain why the word ancient is in here and why this makes sense. I would say our principal goal, the reason this mission exists, is that we are preparing samples to be brought back to Earth for analysis in terrestrial laboratories. Many of the questions that we have about Mars can only be answered with instruments that exist on Earth that can't really in the foreseeable future be flown. And as an example, in the area that I'm most engaged personally, mass spectrometry is a way you learn an enormous amount about, for example, the age of rocks. And a typical mass spectrometer has a magnet on it that really weighs almost a ton. So flying a magnet that weighs a ton to the surface of Mars is not happening, at least for decades into the future. Bring the samples back to Earth rather than flying the instruments to Mars. We also have a mandate to what NASA calls enable the future, which means demonstrate new technologies that could be of use for future exploration, either of Mars or elsewhere. And a lot of that landing capability that we tested falls into that category. In fact, in the early days of the Europa lander mission, there was an idea that we would land, NASA would land a spacecraft on Europa. They were going to use essentially the same technology. That mission isn't going forward now, but someday maybe it will. So those are our goals. I want to explain what this looking for evidence of life is, because it's an unfamiliar thing to a lot of people, how we're going about this and why. This is an image of Gale Crater from the Curiosity rover. It's one of my personal favorite images because there's a huge information content here if you know how to look for it. First and foremost, the surface of Mars today is too cold, it's too dry, and there's too much radiation for life to exist anywhere that we know on the surface. So if somebody says, go look for life on Mars, it's kind of a fool's errand to look for extant life, things that are alive today, if all you can do is probe the surface. There may be life in the subsurface, but especially, and you all will completely get this, that the atmosphere is so thin and there's no magnetic field. And so the combination of solar ultraviolet radiation and galactic cosmic rays really cooks the surface. It's lethal. And the cold and the dry are not conducive to any life as we know it. But the reason I start with this picture is that to a geologist, this is spectacular, because this layering that you see here, now confirmed by rover investigation, is sediment that was laid down by liquid water in a lake or river in Gale Crater. There's no doubt about that. There were lakes and rivers on the surface of Mars from a time period between about 4 billion years ago and 3.5 billion years ago. Sometime after 3.5 billion years ago, there was enormous climate change, and the planet may have occasionally, for very short periods, had water on its surface. But this era in which lakes and rivers were common disappeared, probably because of the loss of the atmosphere associated with the loss of the magnetic field. That's a supposition, but that's what most people believe is cause of the climate change. And what that means today, if you compare modern Mars, cold and dry, with early Mars, and this is of course an artist's conception, lakes and rivers were certainly present. There's no doubt about that. There's a kind of a raging debate as to whether there was a northern ocean. The rock record that might record that is largely gone because it's buried under thick dust. So there's not much to see up here. But up in the highlands, which is this area that you see that kind of cratered here, there was definitely water. So if one is looking for life on Mars, look in the rock record. Do not look in modern Mars. And so that is the central reason that we are looking at ancient Mars. And it's useful to understand, or at least think about, what life might have looked like back then. And of course, everything in the solar system was created about 4.5 billion years ago. And that means that 3.5 billion years ago is not that long after accretion. And we have exactly one example about how far life can evolve in that billion years. That's Earth. So we're going to use Earth as an analog. It's all we have. So I'm not going to try to defend why this is the right thing to do. It is really the only thing you can do. There is a very limited rock record from about 3.5 billion years ago. Of course, most of the Earth's surface has been recreated in the last 3.5 billion years ago by plate tectonics, or has been eroded away. But there are places, especially in Western Australia, where there are sedimentary rocks, little scraps, 100 meters on a side kind of scraps of sedimentary rock from 3.5 billion years ago. And here's what you find in them. This is evidence, the oldest evidence, or let's say the oldest uncontested evidence of life on Earth. It's a kind of a rock called a stromatolite, and it tells us what life on Earth was like a billion years after accretion. What you're looking at here, it's a pen for scale, is a deposit which was produced by microorganisms that were growing on the interface between mud and water in the bottom of a shallow lake or sea. And that the microbes glued the sedimentary grains together. And then, probably because these organisms were photosynthetic, there was a driving force to have them grow higher to get more sunlight. So you get this kind of characteristic bulbous and crinkly texture. And we recognize these because these things still exist. They're very rare, but this is an example of a living stromatolite. Coincidentally, it is also in Western Australia. So 3.5 billion year difference between these two, but this is growing there's a very low tide in a place called Shark Bay. And this is a living stromatolite made by microorganisms that have glued sediment together. So this is the kind of thing we should be looking for. We should be looking for microbial life. And this would be a wonderful thing to look for because it's big enough that you can see it with a camera. You don't need a microscope to see it. So the key point is that 3.5 billion years ago, in all of the scraps of sedimentary rock that are that we can look at that are not completely destroyed by metamorphism, there is evidence of microbial life. So not only was life present in one place, it appears that life had colonized Earth quite well by 3.5 billion years ago. And so the important comparison here is 3.5 billion years ago, life on Earth, shallow lake and sea. That's where it lived. The landing site that we selected, called Jezero Crater, is a 3.5 billion year old lake. So I have two planets that were broadly similar. One of them clearly had life on it. It is a reasonable question to ask whether the other one did. So this isn't really too much of a stretch. And I would say if we do not find evidence of life here, it will tell us something about the ubiquity of the origination of life, which is really, to me, one of the it's the key question about life is does it require extraordinary conditions, or does it happen as soon as you build a habitable environment? So now I want to talk about the landing site and some of its details. So this is another image. You recognize the delta, the 1 kilometer crater. We're up here in the northern hemisphere of Mars on the edge of this giant impact basin. Jezero Crater is about 40 kilometers in diameter. You can see the rim here. The rim is almost 1 kilometer high. And it is a spectacularly obvious example of a lake river system. So you can see the river cutting through the canyon, cutting through the crater rim here. This river extends for almost 60 kilometers upstream. That turns out to be important for what we're thinking about for the mission. And then this feature is a delta. And the delta is produced when the turbulently suspended sediment in the river hits the slack water of a lake that would have extended all the way up to the edge of the crater. When you hit the slack water, the turbulence stops and the sediment falls out. So easily understood, very recognizable delta feature. And this is an artist's conception of what this crater might have looked like. One of the cool things about the crater is that there's an inflow channel and there's also an outflow channel. And the reason that's important is it tells us how deep the lake, that it gives a minimum estimate of how deep the lake was. And it's more than 150 meters. So 40 kilometers in diameter, 150 meters deep. This is a very large lake. It's not a little puddle. So that is a real attraction for us to go and investigate this place. Best estimate, 3.5 billion years old. But I caution everybody that it has a formal uncertainty that is quite small, meaning that it's done by crater counting the density of craters and various features. If you actually consider the real uncertainty, we don't know much about the cratering history of Mars. That's probably uncertain at 500 million years. So it could be 3 billion years. It could be 4 billion years, which is of course a quarter of the age of the solar system. So we're not doing, we don't know exactly when this is. And of course, one of the reasons we want to do sample return is to determine exact ages on Mars. So it's a delta. So let me just say a few words to put the delta in context. This is important not only because it demonstrates that there was a lake here. It demonstrates in a way that is very compelling. A delta is also interesting because it both hosts and preserves evidence of life. So this is a delta from somewhere in Alaska, and you can see the distributary channels, and you're going to see these on the, well, actually, let me go back. If I go back here, you can actually see similar channels across the surface of the delta. So that's the way deltas work, is the water comes down and it forks and deposits sediment. So what you can see in this image from these colors is organisms that are living in the mud flats. So that's intuitive, everybody knows that. And because this is a relatively placid environment, especially when you get out into the front, like you can see sediment being carried out here, it's going to deposit in the shallow waters. It's very gentle. It preserves life instead of, for example, a mountain river, which would bash up evidence, fossil evidence of life. So it is a good place to preserve evidence of life. And this is especially true for organic matter, which of course is a key indicator of life, or it can be a key indicator of life, because this fine-grained sediment, not only the organic matter binds to that fine-grained sediment, it also protects it from oxidation. So this is why your big, oil deposits on the earth are in places like off of the Mississippi River Delta, where you have lots of sediment being deposited and preserving the formerly living things that were also deposited. So Delta is a really cool place to investigate for life. And that's why it was our central target for science exploration if we had landed at the landing strip. I'm not going to go into gory detail about all the instruments on the rover, but I do want to show you a pair of instruments that are completely new for this mission. And they were expressly designed to look for evidence of life. Out here on the turret, so this is a big set of science instruments mounted on the robotic arm, are two instruments. One of them does X-ray fluorescence elemental mapping. This is a standard technique. You'll find it in geoscience departments everywhere. So use X-ray fluorescence to determine what elements are present. And we also have a Raman instrument, which can tell you what minerals are present and can detect organic matter. Now, interestingly, and you might imagine what a challenge this is, the robotic arm we only have one, and our very delicate science instruments are mounted right on a rotary percussive drill for sample collection. So this thing is vibrating very hard as it cores into a rock, and you'll see lots of things like these. These are vibration dampers. So it's a little crazy to have your super sensitive science instruments mounted on a hammer drill, but there you have it. So here's what we could see if we looked at a stromatolite, one of these fossil microbial mats. So this is a visual image. We have a high resolution camera on the arm, so we could get an image like this. But then we can map, using X-ray fluorescence, we can map what elements are present. And in the same area, we can map the minerals and organics. So this is a key way that we hope to be able to identify potential biosignatures, things that could be evidence of ancient life. And I'll say right up front, I say potential biosignatures because the burden of proof is so enormous for life on another planet that I don't think we'll ever be definitive about it, unless there's something that absolutely, totally stands out. These will be potential biosignatures until we bring them back to Earth and they can be subjected to the kinds of analyses that could potentially prove that they are biogenic. So that's the hope, that we find something that looks like that. Let me give you a sort of progress report on what we've done. I showed you where we landed. In much the same way that, a baby has to learn how to crawl and then walk and then run, we had to learn how to operate this rover. And so for about the first 3 months of the mission, we were doing very scripted, careful checkouts. So here we are, first time rotating the wheel, first time rotating the turret, first time driving. Here's the landing site here. And, you can see we drove away from this completely clean landing site. This is a very, very complicated piece of hardware with the need to treat it carefully when you first landed to make sure that everything arrived safely. And it turns out it did. Everything checked out. All the science instruments work. All the actuators work. No issues at all with the long journey to Mars. So that was great. We did that in about the first 3 months. And while we were doing that, we also demonstrated one of the new pieces of technology that is associated with the rover, which is the Mars helicopter. I'm not sure how well you can see this image, but here is the Mars helicopter flying. So this is what you're looking at here is a drone, not at all like a drone that you would buy in a hobby shop. It's in the Mars atmosphere, which is 1% the density of Earth's surface atmosphere. You need a very large blade. And so the blade here is almost 1 meter across, and there are 2 of them, 2 counter-rotating blades. This is a technology demonstration, and what that means to NASA is it was built to simply demonstrate that this could be done as a precursor to future use. So it does not have, at least initially, a science objective. It didn't have to prove that it could do a science mission. It just had to demonstrate that it could fly. Spectacularly successful. The helicopter succeeded on its test flights, and it is now in support of the science mission. We use it to do reconnaissance, to fly out ahead of us and find interesting outcrops, and equally importantly, to find traverse routes that the rover can get across. So it is sticking with us, and it has now lasted about 3 times longer than it was initially designed to. So it's been a great success. It'll be interesting to see what happens in the decades ahead for the development of this kind of technology. Here we are at the landing site, and I'm going to show you first some images that we took early on of the Delta, because we learned some really interesting things about the Delta once we were on the ground. Remember, these cliffs are about 40 meters high. So we call this the Delta front, and this feature here we call Kodiak. I'm happy to explain why we come up with the names that we do. They're probably quite strange to you all, but we call this feature Kodiak. And what it is, very obviously, is it was a piece of the Delta, and it is now an erosional remnant. So this feature is eroding back, and it left this little piece out here. Then I'm going to show you some pictures from this region here, and then from the area here called Artubi Ridge and Seta. So here's Kodiak. This is my favorite image of the mission. It's just a spectacular image. This is about 500 meters across, 40 meters high. And you see these curving features overlain by flat layers. This is a Delta. It is exactly what we expect for a Delta. So imagine you take this feature and you made a vertical cut and picked it up and looked at it. So this is a cross section of the Delta. And the thing that we learned just from this image alone and from the curvature of these beds is that this piece of Delta was growing out into a lake. It's what we call prograding. So that means the Delta is growing out into a relatively stable lake. So this was not a huge surprise. We expected to see this. We did not expect to see such clear confirmation of what the conditions were like when the Delta was growing. So strong confirmation of a lake. We know how deep it was from looking at this. But what was a big surprise is when we looked over to the Delta front, we saw some similar features, but we also saw some features that were very different. And to a geologist, this lens-shaped feature that you see here, which is about 40 meters across, a lens-shaped feature cut into or inside a set of sedimentary layers is exactly what you expect for a river channel cutting down into pre-existing sedimentary rocks. So this is a former river channel, but what's a big surprise about it is when you look at this up close, this boulder that you see here, big rounded boulder, is about 1.5 meters across. You do not transport a 1.5 meter boulder in a little channel like this. You just don't have enough turbulence to do that. Instead, these big boulders must be indication of transport in a flood like this terrestrial image here. And you don't transport big boulders underwater, under lake water. You just don't get that kind of flow. So this is telling us that after much of this Delta formed in a stable lake, the lake must have dried up or largely dried up. And then a raging flood came out and incised a river channel, deposited the big boulders, and then got buried by additional layers of sediment, probably by later rivers. So we're in the future of this mission, we're going to explore what all this is, but it's telling us that there are multiple generations of processes occurring in this lake, which is very interesting. It tells us about the history of water on Mars. So now moving on, this is the area that we landed, and you can see why we landed here. You have these nice smooth rocks and the boulders in the background. These rocks were very frustrating to us because there is nothing on them in their appearance that tells you what they are. Are they sediments deposited in the bottom of the lake? Are they lava flows? What are they? So we spent much of the first 8 months of the mission wondering what they are. And part of the problem with this is that the rocks are coated with dust. The kind of brownish tint that you see here is dust. And there's also a superficial coating of unknown origin. So we can't do the usual thing, just go look at the rock with your eyes and it'll tell you what it is. Instead, we had to abrade into the rock. So we have a tool that grinds into the rock surface. This is about 4 centimeters in diameter, grinds off the dust. You can see how dusty this is. Here's what the target looked like that we abraded in. Very hard to learn anything. We abraded in. This image came down from our microscopic camera that's on there. Big surprise. As soon as we saw this, many of us said, wow, not at all what we expected. Big grains here, millimeter-sized grains in a texture that looks like an igneous rock. So this is either a lava flow or, more likely, because of the grain size, it indicates that it cooled slowly, and it could be a rock that what we would call an intrusive, meaning it was intruded below the surface and cooled below the surface. So that's a puzzle. We pulled out our instruments and used the X-ray fluorescence instrument. And this, I just want to show you a flavor of the data. Next week at the American Geophysical Union meeting, we're going to roll out lots of discoveries that we have, but this is one I can publicly share. Every point that you see is a place where we made an X-ray fluorescence measurement. And when you put all of this together over a 3 millimeter scale here, we can see that this rock is made out of plagioclase, pyroxene, and iron oxide. All of this is consistent with this being a rock of basaltic composition. So it's a relatively unsurprising composition, but it is quite coarse grained. So that was a great discovery. It solved the question of what the rocks were. And we decided that we would collect a sample. So Perseverance carries 42 sample tubes to acquire rock cores or regolith. So here's an example of a rock core. It's about the size of your pinky, size and shape of your pinky. And we drill it directly into a sample tube. Each sample gets its own tube, and then we seal it. So we have 42 of these tubes inside the belly of the rover. And you'll see in a video I'm going to show you in a minute, a little cartoon, how this works. But here you have the rotary percussive drill that I mentioned, and here you have the science instruments mounted to it. So we decided we wanted to collect a sample, and it works like this. So the sample tubes live inside the rover in an incredibly sophisticated piece of hardware I'm going to show you in a minute. So this little clip shows after we have decided that we want to take a sample, and the drill reaches out. It already has a sample tube loaded into the rotary percussive drill. So it's in the axis of the drill. So we reach out. This thing weighs 40 kilograms. So it's a very tricky operation to do this. Rotary percuss into the rock, directly into the sample tube. And now you're going to see the main reason why I show this is to see what happens inside the rover. This is a really amazing piece of hardware. So the goal here is to transfer the sample tube inside. There goes the sample tube into this, what the JPL engineers say is the most sophisticated piece of hardware that has ever been flown for planetary exploration. We need to know what is in that tube. And so we determine whether there is rock in it. we take a picture of it, and we seal the tube hermetically. We make a gas tight seal for each and every sample. And then we take that tube and we put it back into the thing that kind of looks like a beehive here. Every one of these is a place where a tube lives. They are initially empty, and then we fill them up and we put them back in there. So that is a really elaborate dance that has to happen. And the first time we executed this in late August, you can imagine the people that built that piece of hardware, the literally hundreds of people that contributed to that, were very excited. And we were actually watching the data come down. It comes down in bursts. We don't get continuous information. We all got up at 1 o'clock in the morning to see this image. Here you see the abrasion patch, and here you see this fantastic core hole with tailings pile. And then we had to wait about 5 hours to get the data from inside the rover that would tell us that we got sample. So we were very excited when we saw this. Then we saw this. This is looking down the bore of the tube. There is no sample in that tube. So this is literally like looking down a piece of pipe, but you're getting reflections off the bottom. You can see a few little grains in here. Very depressing. We don't know exactly what happened here, but we do know when we looked out over this hole with our camera, there's not a core in here. So we suspect that what happened is the core fell apart, got ground up, and deposited in the tailings pile. This was not good and led to a lot of stress on the team. And the engineering side said to the science side, you need to find us a rock that will not fall apart so we can demonstrate that this thing actually works. Okay, if you were tasked with building this and it didn't work, no core, that is, from an engineering point of view, potentially a disaster. What's interesting is the geologists all said, it happens all the time. Rocks fall apart when you try to core them. There's a big business in geology doing paleomagnetics where you core rocks. Rocks fall apart. Just go try again. So it was interesting to see that the engineers were worried, but the scientists were like, yeah, not a problem. We'll go find you a harder rock. So we decided to go look for a harder rock. And we went to this place called Artubi Ridge. So that the core failure happened here, but we had these beautiful images of this ridge here called Artubi Ridge, which you see here. Here's the ridge. Here it is up close. For present purposes, what I want to say about it is the geologist said the hardest rocks we can find are the ones that have formed boulders on the surface and have stood up to wind abrasion. It turns out that the dominant cause of erosion on Mars is wind abrasion. So we wanted to find a rock that was standing high, surviving wind abrasion. So we went up on top of this ridge and we found this rock here, which is about the size of a briefcase. And we successfully cored it. That was a giant moment. So this was in September. And we know we cored it because now when we look down the tube, we see this wonderful rock inside the tube. And we estimate that it weighs about 15 grams, which was the goal. So big victory. We have acquired now 4 sample tubes with rock in them. So we are well on our way now to meeting the goals of the Mars sample return effort. We took 2 cores here for a reason that I'll describe in a minute. They're right next to each other. Each one of these is a rock core that is now stored on board the rover. And this is my final slide. We are part, the Mars 2020 mission, are part of a 3-mission campaign to bring the samples back. The current thinking involves a joint NASA-ESA effort to do the follow-on missions. So the Mars 2020 rover does not have the capability to bring these samples back. We don't have a rocket on the rover, for the simple reason that this rover is already extremely complicated and expensive. And it didn't make any sense to try to add additional expense and complexity to this mission. So let this mission be a science mission collecting the samples, and then to transfer by one means or another to the rocket. And the way that is currently imagined, there are a bunch of different scenarios, but the sample tubes, about 30 of them, we have 42, so there's a little bit of a down select that's going to happen. About 30 of them will be put in the nose cone of the rocket and will be launched into orbit. So here's what we call the orbiting sample. So that about 30 samples are contained within this sphere. And then a third mission captures this sphere. Seems kind of magic to me. I don't know how you capture something that's the size of a soccer ball in orbit, but apparently this can be done. And then you bring it back to Earth. So this is scheduled to happen later in this decade. And samples will likely be back, if all goes according to plan, in the early 2030s. And what I like to say about that is that's still a decade away. And ever since I was a graduate student, which was a long time ago, Mars sample return has been a decade away. But now we've started. And I think there's a lot of momentum. We're getting really good samples. And I think this has a high potential of actually coming to fruition, that these missions will be executed and samples will come back in the early 2030s. And I think they will be hugely important in two ways. There are a large range of questions we know we will want to ask. Like, how was it even possible that the climate on Mars allowed for liquid water? There are no models that compellingly allow that. And so we hope to learn, for example, from minerals precipitated in the lake about what the climate was like. We also want to learn about geologic time. We want to get radiometric dates. And then the thing that will be most interesting, at least from my personal perspective, is scientists will, for the first time, be grappling with the question, how do you look for life in rocks that could compellingly have life as we don't know it? What would you look for? How would you go about that question? And people have thought about that, but it's a completely different story when somebody is faced with the challenge, here's your rock, go figure it out, go see if there is life in there. And I think this is going to lead to a lot of really interesting technological developments and a lot of fundamental considerations about what life means. It doesn't make a whole lot of sense to look for example, DNA in these rocks, because it's a great way to do it on Earth, but there's no reason to believe that Mars has DNA. So I'm looking forward to when that happens in the next decade. And I guess I'll stop there and see if you have any questions.
Thank you so much, Ken. This was a spectacular set of images. Well, yes, we'll clap at the end. I mean, and it's sort of humbling to be able to see what you've just presented, and it was really interesting to have your expert commentary. I'm sure there's lots of questions, so please put your hand up, or alternatively write a question in the chat. Okay, Uli Bastian, first up.
Proud to be the first. About this drilling, I think I understand why you do it. You want to have the insides of rocks in order not to have them disturbed by environmental effects over this long time. But still, if you would simply, as the Apollo astronauts did, pick up a few, they have an inside as well. Would that have been easier?
I'm not sure I got the question, but I think I did. So the samples that we collected included the rock surface. The core has the rock surface.
Yeah.
The abrasion patch was only used to allow the science instruments to see inside the rock.
Uh-huh.
So we are definitely bringing back both rock interior and rock surface. Was that your question?
I was questioning that complicated drilling and storing and so on. If you would take this whole rock, you also would have, and bring it back to Earth, you also would have surface and interior.
You're talking about why is it sealed in a tube?
Yes,
and not just grabbing a rock.
Why it's drilled at all? Why it's not just picked up and brought back?
Yeah, so I can just give you my sense of well, there are two reasons. One is they are hermetically sealed so that any gases that are in the rock, any minerals that have volatiles in them, will be contained within them. So that's one reason to seal it in a tube. The other, which I have learned, is that the engineers do not like things like rocks because they are very hard to actually understand from first principles. If you take a rock core, they know exactly, what its size and shape is. If you told them, yeah, we're going to pick up some rocks on Mars and put them in a container and bring them back, that is an ill-defined problem. So there's a lot more control with this. And the other aspect of this is the surface of the rock is undoubtedly bathed in ultraviolet radiation. And so we wanted to get down below that. So if you just picked up a little rock like this, it will have been quite exposed to radiation. You get down, you don't get rid of the galactic cosmic rays very much, but you definitely get rid of the solar cosmic rays and ultraviolet by going deeper in the rock.
Okay, thanks.
Ralph, please go ahead.
I have a very naive question. So this was great. I'm wondering, how far can you actually go? If you say you have a decade, can you reach this cliff, the end of the delta? Is it a question of finding a path? Is it a question of having enough energy available? Is it?
Yeah, let me show you what we're thinking of doing. So we selected this landing site for the reason that I said that there's a great a delta here.
Mm-hmm.
Because we didn't land here, we wound up exploring this way. And shortly, we're going to turn around. We cannot cross this. It's sort of, I have to say, I was a bit depressed when I realized that we're going to have to spend several months driving around this feature to get to the delta, but we will. So in the spring of next year, I imagine we will arrive at the delta front, and we have already charted out a route that brings us up this way, crosses over here. So we'll explore the delta here, looking at what we are. These turn out to all be igneous rocks. That's our conclusion. These rocks are undoubtedly all sedimentary. So we'll explore these. And one of the really interesting things, which I did not point out in the images of the delta, this surface is littered with giant boulders that originated in somewhere way up in the headlands, headwaters of this river. So those will be really interesting for us to explore. And then if the mission functions as we hope it does, we'll actually climb out of the crater and explore areas beyond this crater. So we have a route all drawn out. We know it is traversable, and it's pretty ambitious. It's 30 kilometers of traverse. So we're going big on, we're going big. And that's kind of a different approach than the Curiosity has used, because they're not preparing samples for return. They're simply using their science instruments. We are trading off scientific depth for diverse samples. So our goal is to traverse the landscape and collect a big diversity of samples to be brought back.
Okay, thanks.
Lauren Baylor Jones, please go ahead.
Yeah, hi. So my question was about the 1.5 meter size boulder that you mentioned. You were saying that it was evidence of basically a river having the turbulent flow having deposited there. This may be a naive question, but it just seems surprising that it would still be there after 3 billion years. I mean, I know that there's not a lot of tectonic activity on Mars, but I would have thought, given the sand and the winds and enough time, that it seems unlikely to remain over that time period.
Okay, let me get to the picture here. So
Yeah,
this, couple of comments about this. So this is not what the shape of the delta would have looked like when it was deposited. It would have been deposited in a very shallow gradient extending way out into the lake. The cliff is produced by erosion. So this feature is being eroded back. And it is disappearing. This is just an instant in time. But what was, a puzzle to us, and we still don't really understand it, this boulder, when you look at it, you can see by the way it casts its shadow, it's sort of protruding out of this lens-shaped feature. It is going to fall. It's like, why is it stuck in there?
But that's what I was thinking. It seems rather fortuitous to have found it at that time.
Right. Yeah. But the reality is these boulders are everywhere.
Yeah.
They're big rounded boulders all over And I think what has happened here, when you see the big boulders up here, they're what we call a lag deposit, so that this was much taller at one point. And the fine grained material, which is mostly sand and smaller particles, has been eroded away probably by wind. And it's just leaving these boulders in this lag deposit. So these big rounded boulders up here are evidence of the same phenomenon higher up in rocks that are no longer here. And I would say this is one of the hardest things for all of us collectively to get our head around, that this landscape has been sitting here for 3.5 billion years. And the only substantial thing that is happening for most of that time is wind. This is not the way things work on Earth. You know, it's a landscape that's quite different in its fundamental processes than anything on Earth.
Okay, thanks.
Okay, Hans Ludwig.
Hello. I hope you hear me.
Yes.
Good. Whenever I see these nice images from Mars, I'm wondering, this is perhaps a naive question, about the colors. How serious can I take the colors that are often visible in these images? You yourself showed landscapes where we saw rocks with a bluish tint and reddish material. Is it a realistic impression, or is it still a bit of, choice of color scale and so on and so forth?
So you touch on an interesting topic that I should have made a disclosure. We acquire these images in more or less natural color, and everything has a pinkish tint. And I could show those; they would look basically the same. But you're correct; the sky is not blue on Mars; it is pinkish. And so these images, most of us find that the images which have been adjusted by a kind of standard process, whose goal is not to mislead people. The goal of adjusting the colors is to help us use our instincts developed in looking at rocks on Earth to try to make it look like rocks on Earth are illuminated in a certain way with a certain color, temperature, et cetera, et cetera. Yeah. So these are adjusted to allow us to use that experience. But to be honest, I will also say I find them more visually pleasing. So I tend to use the ones that have the bluish cast instead of the pinkish cast because I like the way they look. But it is true that a lot of geology at this level is looking at rocks and saying, yeah, that looks familiar to me. Rather than trying to simply capture what Mars is actually would look like if you were standing there.
Okay, thank you.
Okay, I think we just got time for one more question. If I can just ask Mikhail Zabertev.
Okay, do you hear me? Yeah, one technical question about this heating, cooling of the system. When you are drilling, do you see the temperature variation due to power consumption or not? And a second question, in the future, do you have any idea where the future mission will collect your collected samples?
Okay, so I think you're asking, are we dissipating heat into the rock?
Yeah.
Yes, absolutely we are. It's a rotary percussive drill. It is hammering quite hard. And we had a requirement when we developed the drill to limit the amount of heating. And we did an experiment where we used a mineral that we know decomposes at 62 degrees. I think it's gypsum dewaters at 62 degrees. And what we found is that most of the rock stays below 62 degrees. This is in terrestrial testing, stays below 62 degrees. The surface, it turns out when the rotary percussion works, you actually wind up sometimes breaking the core into little discs, and they spin relative to each other. So there's frictional heating. So most of the rock stays, we estimate it stays at something like 10 degrees, which is about the maximum temperature that these rocks will see on a sunny day. Some of it does get hotter. It's inevitable. And then I didn't quite catch the second question.
Do you have idea where this how to say, where the future mission will find this rover to pick up the samples.
To pick them up from the surface of Mars. Yes, good. So I told you we collected 2 copies from that one rock, and this is our strategy. We are going to, in about 2 years' time, we are going to put down 1 copy of each sample on the ground and keep the 2nd copy. And this is a way to ensure that the Mars sample return missions have a target should Perseverance become disabled without putting the samples away. Once Perseverance is disabled, there is no getting the samples out of the inside of it. So the goal is to put something on the ground as a target and then carry the rest. And then what will happen, it will be up to the future missions, but we will then have multiple opportunities. The future missions could either pick them up from the ground with a fetch rover, meaning that they'll drive over and pick up the samples and bring them back to the rocket. Or if Perseverance is still alive, Perseverance could be carrying them. And we've just been looking at concepts where the lander that has the rocket on it can have an arm that interacts with Perseverance, and Perseverance essentially feeds those tubes to the arm, and they put them in the rocket. This is a very complicated interaction. It's not something that NASA has done before, where missions separated by a decade need to interact with each other. And so it's an interesting area of coordination that we are finding our way through.
Okay, thank you.
Thank you.
I think we'll wrap up the formal question session for the moment. Ken has kindly agreed to stay on after the formal end of the colloquium, so we can deal with question in the chat and any further questions then. Before thanking Ken, I'd just like to share my screen and advertise next week's colloquium, which will be by Anna Bonaca, who is going to tell us all about the assembly history of the Milky Way. And I'd like to point out that Anna will be actually physically visiting Heidelberg next week. So please do take the opportunity of getting in touch with her or with her host, Didier Krutzian, who will be glad to arrange a meeting or a discussion. So I think now we just thank Ken by opening our videos and opening our microphones. Let's give Ken a truly wonderful thanks, and we look forward to the future of Story, having had our appetites whetted in this way. Thanks, Ken.